So this afternoon, we are here together to do some mathematics together, of course, as usual. We do need to say a big thank you to Trinity College here in Cambridge for funding the webinar this afternoon. So it's all free for you to join. We are going to be working on a bit of mathematics as we go, so we will be inviting you to contribute to the chat as we go along. Do feel free to post general questions there as well. Before we get going on the focus of today, which of course is working systematically, we'd like to just go back to give you a bit of background. Now, you are very welcome whether you've been to an NRICH webinar before. Maybe you're joining because of recently becoming a problem-solving school as part of our initiative. And I think one thing we'd really like to make clear is that all the resources that we talk about today are freely available on the NRICH site. And if you would like to find them quickly, the best thing to do is to click where it says Problem Solving Schools in the top menu of any NRICH page, and then scroll down and click on the right-hand box where it says Resources and Professional Development. And at the bottom of this page, you can see all our new Working Systematically resources, which we're going to be sharing with you in more detail today. But before we get to the Working Systematically point, I'd like to just take a little bit of a step back. Those of you who have been on professional development with NRICH before are hopefully becoming a little bit more familiar with this model. So this is a model that we use as a framework as we're developing tasks for the NRICH website. It was created by Kilpatrick and his colleagues back in 2001. And we like to refer to it as the rope model. So the rope model is a way of thinking about the characteristics that we would like to develop in young mathematicians. Now, as you can see, the rope model consists of 5 strands. Now, 2 of those strands, conceptual understanding and procedural fluency, I think we would see in mathematics classrooms around the country. Most teachers are very focused on understanding and fluency, so there's no surprise there that those 2 strands help to develop a good mathematician. But at NRICH, we also believe that these 3 other strands are of equal importance. So let's have a look quickly at productive disposition. So by that, what we mean is, do students think that mathematics is a worthwhile subject to be studying? Do they understand that actually, you're not born good or not so good at mathematics? It's up to you to apply yourself, to work hard, and then you will become a better mathematician. And do we give those messages in the classroom? So that's the productive disposition. Are we giving students those opportunities to be curious about mathematics, to work collaboratively, become more resilient and more resourceful? These 2 strands that we haven't talked about yet, I'll talk about together. So strategic competence, this is about your toolkit of strategies when you're faced with a new problem that you may not have seen before. Do you have skills that you can draw on to help you tackle those problems? Along with adaptive, can you reason? Are you able to explain what's going on? Can you begin to convince other people of your reasoning, and even go as far as proof? So as I say, these 5 elements we believe at NRICH are of equal importance, and so we're thinking about all 5 as we create resources. Now, recently, you may well know that we have had a bit of a website revamp, and what we're trying to do now is reflect all 5 of those strands within the structure of the NRICH website. So if I click here on the teachers menu and choose the secondary teachers landing page, you can see that the boxes, the 3 left-hand boxes, if you like, are helping to gather resources in a way that reflect the rope model. So our curriculum-linked problems, that's the place you would go if you're really wanting to focus on understanding and fluency in particular. If I look at the 3rd box, developing mathematical mindsets, that's akin to our productive disposition. So the curiosity, the collaborative, being collaborative, developing resilience and resourcefulness. And then those adaptive reasoning and strategic competence strands, we've decided to break down a little bit further to help you in the classroom. And we've popped this under a developing mathematical thinking heading, banner, if you like. And if I just scroll down the page here, you can see that what we're trying to do is we're trying to reflect the kind of process that you might go to when you're faced with a new problem. So to start with, you might do some exploring and noticing, and you may well have joined us last time for our webinar where we focused on that first aspect. Having done some exploring and noticing, then it's the time to work a bit more systematically in order to conjecture and generalize. You might well then use some visualizing and representing before you go on to some reasoning, convincing and proof. So this is a journey through the mathematical process. Now, as I said, last time we focused on exploring and noticing. Today, we're very much about working systematically. And just a bit of a health warning. That means that we're going to try to be quite strict with ourselves. Yep, Charlie, we really are only going to try and focus on the working systematically aspect of a task. So we will stop you mid-flow. That may be frustrating, but we hope you will continue thinking about the mathematics after the webinar, and that you will join us for our subsequent webinars to explore the process further.
Yeah, we hope that it'll be obvious that after you've worked systematically, that would be the springboard to doing some conjecturing and generalizing. So we'll whet your appetite, we'll tease you, and hope that that will encourage you to come to the next webinar. I suppose one other thing to mention is, one of the reasons we like the rope model is that all those threads seem to be interlinked and working together and supporting each other.
Yes.
And like Liz said, on the website, we've got the 3 sort of divisions. But I think what people like about NRICH problems is that the very best NRICH problems are offering students opportunity to rehearse their understanding and the fluency while having to think strategically and reason and maybe prove, and hopefully have a positive experience that makes them feel, because either we've been encouraging them to work collaboratively, or we started with an activity which is tapped into students' curiosity. So they're in separate sections on the website, but we're trying to remain true to this. Whenever we write a problem, we're trying, our problems will appear in all 3 areas. So there'll be the problems that we look at today would be tagged with curriculum tags, but as well as with thinking tags, well, the systematic tags in particular, and there'll be a mindset tag.
That's right.
At the same time.
That's right. I think it's time to do some maths, Charlie. Okay. So what we're going to do is we're going to offer you a number of tasks which lend themselves to working systematically in slightly different ways. We'll have a go at the tasks, and we will then share the guidance that we've created on the site and talk through that a little bit and show you where you can go to find tasks that will be perfect for your own students to practice working systematically. Okay, Charlie, so the first task I believe we're going to have a go at is the number jumbler. And actually, if you were here last time, we looked at this task, didn't we? We started this task when we discussed exploring and noticing. So we're going to be quite careful today. Okay, so shall we have a go at the task?
Yes, and so last time we just did the exploratory stage. And we will, I think, come back to it in future webinars when we try and explain what's happening. But let's think about how we could approach it systematically.
Okay. So join in this task at the moment wherever you are, and I'm going to join in as well. So we're going to start by choosing any two-digit number. So I think I'm going to go for 32 as an example. And then we'd like you to add together the 2 digits. So in my case, that will be 3 and a 2, so that'll be 5. And then you're going to subtract the total of the digits from your original number. So that means I've got to do 32 take away 5. Okay. Right, so 32 take away 5, for me, that makes 27. Now, once you've got your ending number, then you've got a result. We'd like you to find that number on the grid here and look for the little picture, the icon to the right of your number, and really focus on that. So I am focusing very carefully on 27. And we're going to jumble up those numbers in our number jumbler. What is going to be revealed?
That's what you said you were looking at.
That's the heart symbol was the one next to 27. How about those of you participating? What happened for you? Interesting.
Everybody seems to have got a heart.
Everybody seems to have got a heart. Interesting. So Charlie, I guess what we could do at this point, we could do some exploring, and we could do some more exploring, and we could just choose some.
Yeah, so you chose
other
32.
I chose 32.
You could try choose 75 next time. You could choose 16. You could choose 91, and that would be a fairly sort of random way of approaching this.
Yes.
So one way of working systematically could be to just make a very small change. So what I want you to do, Liz, is you started with 32.
I did.
I want you to tell us what would happen is if instead of starting with 32, you started, it doesn't matter whether you go one up or one down, but I'm going to get you going down.
All right.
So if you started with 31, what would you end up with?
So if I start with 31, I have 3 and 1 to add together to 4, make 4. So I'm subtracting 4 from 31. That still leaves me 27.
Okay.
Okay.
Which is what you got when you
Which is what I got when I started with 32.
Okay, so take another one.
Okay,
what happens?
So start with 30. So 30 this time, I'm taking away 3. I'm still getting 27. So, okay, am I always going to get 27?
Okay, so this is the beginning to conjecture that because you've looked at numbers which are very, very close to each other, you notice something that you wouldn't have noticed if you'd been selecting numbers quite randomly.
No.
Do you want to try to keep going down?
Okay, so this time 29. So if I add 2 and 9, I get 11. Oh, wait a minute. This is going to be different. So 29, take away 11, that's 18.
So before you used to get 27, now you're getting 18.
Now I'm getting 18.
What happens if you take another one away?
So 28, take away 10, 18.
So there's something going on here that you were getting 27, 27, 27, and then you've leapt from 27 to 18.
Yes, there's been a shift, hasn't there?
And this might be quite surprising, but you're surprised because you can notice that something either unexpected has happened, and you notice it because you've made very small changes. So one way of working systematically is rather than choose numbers very randomly, and we could have been going up from 32 rather than down, it doesn't matter. But one of the suggestions we've made in our guidance is that making a small change often gives you an opportunity to gain some insights and ask questions.
Exactly. And it's I think you often talk, Charlie, about questions bubbling up, don't you? And the questions bubble up much more quickly. I think they just reveal themselves more quickly if we've made those small changes. And
you feel like wanting to test things.
Yes.
Which is what you do once you've made a conjecture.
Absolutely.
But that will be in the next webinar.
Yeah.
So we'll move on.
We're going to move on. Let's have a quick look at the guidance then, just to show you how we've structured it and why. So I'm going to go back up to the problem solving schools section. And if you remember, what I did is I went down to the right-hand box, resources and professional development, and this is giving you all the resources we've created recently as part of our problem solving schools initiative. So on the left-hand side at the bottom, we've got some guidance about working systematically. We will add the recording of today's webinar to the top here. So what we're saying is that, mathematicians search for structure by working systematically. By working in this systematic way, then underlying structures are revealed. And the mathematical word is all about structure and order, isn't it, Charlie?
And that's why we ask students to look out for patterns, because we expect there to be some order and structure, and rather than a chaotic kind of world.
Right. Exactly. And I guess what we've done here is we've collected together some different problems, some different NRICH problems, which offer different ways of working systematically. And we hope that by doing this, it'll give you opportunities to talk explicitly about what working systematically might mean with your students, and to offer them new problems for them to try out these approaches for themselves. So if I just scroll down the guidance, what we've done is we've sort of tried to categorize the different ways of working systematically. So what we've just been doing, working on the number jumbler problem, is this idea of making small adjustments to go from particular examples in order to give that springboard to conjecturing and generalizing. Now, we're not going to look in detail at problems from the next two sections, but we are going to look at a problem which encompasses both. So just as a quick overview, we think also that one way of working systematic is about creating a list in a very ordered way. So ordering as you listing in an ordered way is a better way of phrasing it. Quite often, that's because you're being asked to look for all possibilities. And so having that system, that means that you know for certain you haven't missed any out.
So even though we're not going to talk about this, we do suggest you may find it useful to look at. We've listed some problems that require students to list in an ordered way. And it can be particularly useful for students to do this when they're doing some work on probability, for example, where they're trying to work out the probability of something happening. And in order to do so, they need to know what the total number of possibilities is. Exactly.
So that's the second way that we believe it's useful to work systematically, in a slightly different way. Then another way that you might work systematically is by breaking a problem down and trying each part separately. Now, the problem 2 and 2, let me just show it you very briefly so that you know what we're talking about. It is like this, where each letter stands for a particular digit, and we are asked to find all the possible solutions for this what's called a cryptorhythm. Now that seems like an unmanageable task, but actually by breaking it down, it becomes more manageable. So for example, you might break it down by focusing on the possible values for t. Alternatively, you might break it down by focusing on the possible examples for the letter O. And we have outlined both of those approaches. I just lost the place here. Here we go. We've outlined how you might do that in our guidance here. We've offered you a sort of an example of what that could look like working on that task. So we're going to share with you now another problem which will give you a flavour of both the listing and breaking down aspects of working systematically. It's called M. Now, Charlie, I think at this point, we're going to stop sharing the screen and maybe share with the visualizer instead. Just put this on. Okay. Do you mind moving your sheet down a tiny bit? Brilliant. So we've got a problem here. We have 5 whole numbers. We're told that the mean is 4, the mean of them is 4, the median is 3, and the mode is 3. So Charlie, I might ask you first. I mean, could you find an example? What do you know? How might you go about starting this problem?
Okay, so if the mean is 3, they're all going to have to add up to 20.
Because there are 5, absolutely.
And if the median is 3, I'm going to need a 3 in the middle.
Okay, that's great. Yep.
The mode is 3, so I need a few 3s. Okay, so I know that 3 3s add up to 9, and I need another 11 to make a total of 20. So I could have 5 and 6, for example.
Nice.
You did say stick to whole numbers, didn't you?
I did say stick to whole numbers. Brilliant. So that's one solution. I might ask you if you could find another solution.
Yes, I imagine.
You sound more doubtful.
Yes, I could keep those 3s, take 1 away from that.
Oh, yeah, that's nice.
So I need another 12 here. Let's say 4 and 8 is 12.
Okay.
Okay. So
another solution. But then what if I said to you, you know, I'm going to challenge you, Charlie, to find all the possible solutions. Okay, 5 numbers, mean 4, median 3, mode 3. So now we've got to think about finding a systematic way to work so that we make sure we find all the possibilities. So Charlie, what might you do?
Okay, so there was that strategy that you mentioned just now about breaking the problem down
Yes.
into parts. So one thing I could do is say, okay, what would happen if I just have 2 3s?
Okay.
I must have at least 2 3s.
Because the mode is 3. Yes.
And then later on I can try 3 3s and then 4 3s and then
etc.
So I might start with 2 3s and see what happens.
Okay.
And if I've got 2 3s and one of the 3s has got to be in the middle,
yeah,
then the other 3 could be there, but it could also presumably be there. So
yeah,
with 2 3s, either they're in second and third position or they're in third and fourth position.
right.
And that's okay. So now I can start thinking, okay, what could go on either side of these? And I don't know how many there are going to be, but okay. So if I've got 2 3s in positions 2 and 3, I could have a 1 first of all.
Okay. So that means we've got a total of 7.
So I need another 13.
Yes.
Another 13. 4 and 9.
Yeah, that makes 13.
Or if I make the 4 one bigger, I make the 9 one smaller.
Yes, that would also
Or
work.
if I make the 5 one bigger, I make the 8 one smaller. And then I'm going to have to stop because
you'll get 7 and 6. Yeah.
I'm going to repeat.
Yeah.
But I could have started with 2.
Okay, yes.
Instead of a 1. Then up to 8.
8. So now we need to make a total of 12 with these 2 numbers.
12 is 4 and 8. I didn't draw enough sufficient. Okay. 2, 3, 3. I could make this one bigger.
Yes.
And this one smaller.
Yes.
And then I've got to stop because the next one would be 6 and 6, which would be 2 modes. And I haven't.
You haven't been told you've got 2 modes.
So all of these have 3s in second and third position.
Nice.
And now I could do something similar with, oh, I don't think there are going to be so many here because I'm going to have 1, 2, and then that determines that. That adds up to 9. That's going to be 11.
Right, because if I had 1, 1, we'd have 2 modes. Yeah.
So I'm fairly convinced that those are all the possibilities with 2 3s. But we could have 3 3s.
Yes.
4 3s. And I'm going to write 5 3s, but I know that's not going to be possible because the mean is not going to be 4.
Exactly.
So I know. So how about everybody having a go?
We'll give you a few minutes. Yes.
Where could the 3 3s go? How many can you find all the possibilities? Stick them in the chat.
Brilliant. Would you mind revealing just those details again? Brilliant. Just so we've got those. So 3 3s. Have a few moments. thank you to those of you who've been posting on the chat. I'm going to stop sharing Charlie's jottings, and instead we're going to go back to the NRICH website, because we just want to show you that in the guidance, here we go. If I just scroll down here, you can see that, that we have written up some of what Charlie already did. So if the if the 2 3s are in positions 2 and 3, and we've listed just exactly in the way that Charlie did with you. If the 2
Oh, it looks like I missed one, maybe. No, maybe not. No. Okay.
And so, you know, you can look at these in your own time. So we're not going to go through all the solutions here and now. But I think one of the important things to say about working systematically is that there are multiple ways to work systematically on a single problem, of course. So Charlie, you articulated very clearly that what you did was you started with 2 3s and you broke it down so that you had your 3s in position 2 and 3, and then in 3 and 4, and then you looked at the possibilities with more than 2 3s, and you worked in a systematic way in that sense. But an alternative way to work systematically on this task would be to think about when we are listing the numbers in numerical order, we could break it down by thinking about all of the possibilities that start with a 1. So we know still, as Charlie said earlier, that the 3rd number, if we're lining them up in numerical order, has to be a 3. So if given we've got a 1 at the beginning and a 3 in the 3rd position, then we can do some similar listing, just like Charlie did, but finding all the possibilities that start with a 1. And then similarly going on to all of them that start with a 2. And then we've invited you to convince yourself that there are 3 solutions starting with a 3 as well. And of course,
it just makes the problem much more manageable by sort of chunking it like this.
Absolutely.
When like the example of 2 plus 2 that you showed earlier.
Exactly. So and you know, of course, in the classroom, different students might use different strategies, and they will use perhaps ways of breaking down the problem that we haven't demonstrated here. And I think our challenge, perhaps as teachers, is to really try to engage with students' ways of working systematically, rather than assuming that everybody's got to use the way that we are comfortable with. Okay, Charlie. So, shall we move on to another problem? So. This time, we're going to share with you another interactive task, which we feel lends itself to working systematically in a slightly different way again. This one's called Charlie's Delightful Machine. And in this task, when we enter a number in the interactivity, one of the bulbs may light up, one or more of the bulbs may light up. And it's our job to figure out why each bulb is lighting up. So what is the rule that is determining whether each light lights?
And it would be nice to see whether we can get all the lights to light up, all the bulbs to light up at the same time.
Absolutely.
Okay,
so here we go. We've already got a 0 entered, and then we can see that none of those. I'm just going to scroll down a tiny bit so we can see all the interactivity.
So I suppose a systematic way of working is just to increase the numbers by 1 each time.
Yeah, this is a good point, Charlie, because we might just enter any number. We might enter our favourite number, any number we like. And so we're going to get some information, obviously, about whether that particular number lights all or one of the lights. But that's going to be really hard to determine the rules.
Okay, so let's go up by 1s.
Okay, let's go up in 1s. So if I pop, oh dear, sorry. If I pop 1, okay, we've got green lights up.
Just click on the plus sign.
Oh, good idea. That will make it much quicker. Now, as I am determining this, Charlie is doing some scribbling for us, which we'll come to in a second. So, okay, 2, nothing. 3, nothing. 4, blue.
Okay.
5, green. 6, yellow and red. Oops. Oh, sorry, I went too quickly. 7, nothing. 8, nothing. 9, green. 10, nothing. 11 blue. 12 nothing. 13 green.
Green seems to be appearing quite often.
Well, that's interesting, isn't it? Yeah.
Okay.
And at the moment, if I was just doing this and not noting anything down, I would be finding it very hard to keep track of what's going on. 14 nothing, 15 nothing, 16 yellow. We haven't had very many yellows, it feels. 17 red and green. 18 blue.
So there, 16, we had 3 light bulbs all at the same time.
Oh, yes.
But we're yet to see.
We haven't had all the 4. No.
But at least we know that 3 can be lit at the same time.
19 nothing, 20 nothing, 21 green. Should we just have a few more? 22 nothing, 23 nothing, 24 nothing.
I've come to the end of my page.
Okay, let me share with you what Charlie has been scribbling to give you a sense of this, of another context, another way of working systematically. And I'm sure many of you would have been doing a very similar thing. Charlie, would you like to talk us through what you've done?
Okay, so in the guidance, we've talked about, can I remember what we've talked about? On this page, we've talked about, using recording to capture results in a structured way. And we notice the green, so I've got yellow, red, blue, and green. I've got the numbers from 0 to 24 that and I can see, and I've just ticked green lit up at 1, not at 0, at 1, 5, 9, 13, 7, I think, was it 17? It should have been 17. Can we?
Oh, we can go back. Should we go back?
Well, yeah. We don't stop sharing.
I'll go back and check. Here we go. 17.
Yes.
Yes, was green and red. Sorry, did I read that out wrongly?
No, it was.
I possibly did, you know. Yeah.
Okay.
Okay.
17, and then I think, and all of a sudden, can I just check that everyone can see my screen still?
Yes. Yes.
Okay, I hope so. It becomes very clear that the green is lighting up every 4 numbers, and that all the numbers are 1 more than multiples of 4.
Yes.
So 1 is 1 more than 0, 5 is 1 more than 4, 9 is 1 more than 8, 30, which is why I knew I'd made a mistake at 16. So that's quite nice. I can say something here about green always being sort of, I might write it as, I'll write it up here at the top.
That would be great, yes.
As sort of 4n plus 1.
Yes, nice. So 1 more than a multiple of 4, as you said.
And I think if you typed in 401, you could just check. I'm not going to ask you to because, but so we're ready. We could conjecture.
We can conjecture.
Because we've noticed a pattern. I was also intrigued by the yellows. We had 6 and 16 for the yellows.
Yes.
So my conjecture is that I don't think yellows and green will ever light up at the same time.
Oh, that's interesting. I guess, so green we're saying is 1 more than a multiple of 4, which is always going to be odd.
And yellow is always 6 more than a multiple of 10, which is always going to be even.
Right.
So straight away, we are noticing, what might be more interesting maybe is, let's look at the blues.
Yes.
I think we had, if I wrote this correctly, 4, 11, 18.
Okay. So there we are, as you say, sort of going up in 7s. So 4 more than a multiple of 7?
4 more than a multiple of 7. 7n, 7x, I don't want to use the same n.
Yeah.
Plus 4.
Right.
Okay. I know that 42 is a multiple of 7. If I add 4 to that, I'm going to get 46.
Which will light up yellow.
Which should light up yellow, because the yellows are always 6 more than a multiple of 10.
Nice.
I'm not... okay.
We're going into conjecturing and things now, aren't we?
And we know it's going to work.
We know it's going to work, yeah.
But,
I think the point here, Charlie, is that we could have just written down, you know, in a quite a haphazard way, which lights lit with different numbers. But the fact that you have structured your recording in this way, you've written this very clear table, allows the patterns to be so much easier to identify, and therefore we're able to get at the structure of the problem much more easily. Yes. I think.
So
yeah,
it's about working systematically, but also about recording in a way that you used a word that reveals the structure.
Yes, exactly.
We've got one more problem.
One more task. Let's stop sharing your table, and this final task we'd like to share with you is one. There we go. It's called Pick's theorem, which some of you may well know already. We have some shapes drawn on a dotty grid here, and we're being told that we can describe the shapes using 3 different variables. We can talk about the number of dots on the perimeter, which we're going to call P. We can talk about internal dots in the shape, which we're going to call I, and we can talk about the area of each shape, A. And we could just check that we could calculate those 3 values for each of the shapes we've got drawn. But the interesting question that we are given as a challenge, Charlie, here is, can you find a relationship between these 3 variables? I mean, that sounds really open, unmanageable at first.
But it'd be quite nice to be able to know that if we draw a shape where the vertices are on the dotted grid, that by counting the numbers on the perimeter and counting the numbers inside of dots on the inside, you can work out the area instantaneously.
Yeah.
Because we know how to work out areas of rectangles and triangles and things like this, but when you've got a very irregular shape, this would be...
That would be amazing. It seems
Why weren't we taught this at school? It shows our age. Okay. So here again, we could be systematic. Can we show what I've got on my table?
Yes, indeed.
So the final strategy, the final example of working systematically that we want to demonstrate is this idea of keeping some things fixed and changing others. So in a way, we did a little bit of that with MM&M.
Yeah.
But here's an example, and I've chosen to focus on shapes where there are 8 dots on the perimeter. And I drew a shape. You can see this 3x1 rectangle, and it's got no internal dots. Actually, I'm going to come closer so that it's a bit larger.
Visible. Yeah, good idea.
Can I do this?
It's so counterintuitive moving these things, isn't it?
Okay, I hope that's slightly clearer.
Yeah, that's good.
Yeah, is that in focus?
I might just try and twiddle.
So when there are no internal dots, the area is 3. So I then thought, well, can I draw a shape where there's just 1 internal dot? And I drew a 2x2 square, and the area was 4. Do you mind just lifting that just a touch? I then drew a shape with 2 internal dots, and the area was 5. And 3 internal dots, and the area was 6. And again, keeping a bit like you did with number jumbler, where you were just making very small changes.
Yeah.
I can see that adding an internal dot adds 1 to the area.
Yeah.
And I mean, we haven't yet proved that this is always going to be the case.
No.
And if you come to a webinar sometime in December, we may revisit this problem and discuss how you. But that seems to be a really good way of working systematically. And as Liz, as you said, there isn't just one way of working systematically.
No.
So we could, for example, should cover all this up, is focus on, this is so counterintuitive, okay. It's because you got it done. Okay, no, good. Okay, so we could think, okay, what if I keep the number of dots on the inside fixed and just change the number of dots on the perimeter. So my first shape just had 4 dots on the perimeter and an area of 3. And then I drew a shape with 5 dots on the perimeter and a shape with 6 dots on the perimeter and carried on. And here, the area increased by a half each time.
Lovely. And that's so apparent, isn't it, when you do it in that systematic way? Yeah, it leaps out at you.
Yes. And a third way that we could have worked, and I've got some scruffy bits of paper, where what I did is I fixed the area, and the example that I chose was area equals 6, which is what we put in the guidance as a suggestion. You might want to try this. What happens when you have an area of 6 and no dots on the inside? How many are there on the perimeter? What happens if you have 1 dot on the inside? What happens when you have 2 dots on the inside? What happens when you have 3 dots? What happens to the perimeter? And all of a sudden, one can start noticing how one change affects the other.
Right, exactly.
Conjecture, then go on to explain why all this is happening.
Yeah.
We've got 5 minutes left, and I'd quite like us to revisit where everybody can find.
Yeah, I think that's a really
and maybe
good idea,
return.
Charlie. So let's go back to the NRICH website. If we go back to our guidance page.
Can we just go back to problem solving schools just to
Good
make
idea.
sure everybody knows?
Okay, so we're going to the problem solving schools menu in the top bar. And if we scroll down the page to these 4 boxes in the resources and PD section, these are the resources we've created so far. And the guidance
and if anybody didn't come to our Exploring and Noticing webinar about 2 months ago, there is a link to the video of that session.
The webinar, absolutely. Yeah. So this is the guidance we've been talking about with our different ways of working systematically. And if we just scroll down to the bottom, just to let you know that for Pick's theorem, this idea of changing 1 variable at a time to reveal the structure, we have uploaded those images we've just been showing you here. So they're part of the guidance to give you that that sense of what we mean. So I think, is there anything you'd like to say?
Well, yes, and for all the examples we've done are on this page.
Yes.
And in each one, I think we've left a question to encourage you to go and do a little bit of work. We haven't done all the work for you.
Not quite everything in most cases, I think. Yeah.
But we've also added problems.
I was just going to say that, yes. So of course, the particular problems we've been working on to illustrate ways of working systematically may not be completely suitable for the students you're working with, but what we have done is we have put links to problems underneath each section, and we've tried to indicate the rough age, suitability of those tasks. So we hope that even though they may not be able to tackle the problem that we have exemplified for you, there are similar problems at an appropriate level, so they could apply the same kind of approach to working systematically. And we hope the examples that we've given will enable you to support students as they work on those tasks more effectively. I think that brings us to the end of what we'd like to say about working systematically, Charlie.
In previous webinars, we've always done put some links to people or articles that have influenced our thinking.
Yeah, good point.
And in this case, there are a couple of links John Mason, Leonie Burton, and Kay Stacey wrote this book, Thinking Mathematically. So there's a link to that book, which has been very influential in the way that we've approached rich task and so on.
Mm-hmm.
And I found this book particularly interesting as well. And again, we've got a link to it that you might want to go back to and refer, because again, it sort of breaks up what it means to solve problems. And if we're clearer about what we do when we're solving problems, it'll be easier to understand where students get stuck,
That's
or
right.
why they get stuck, or what they could do differently to get
That's
unstuck. Right. It's not that we don't want them to get stuck. I think getting stuck is part of being a problem solver.
Absolutely.
But trying to figure out what strategies they can use. This business is about being resourceful.
Yeah.
What ways of, well, I mean, working systematically, for example, is one way of being able to make progress in a more efficient way. So those are two books that you may want to dip into, and hopefully available secondhand quite cheaply.
I'm sure they would be. Well, thank you very much for participating on the chat. We really appreciate it. I noticed that a couple of general questions have come in, which we will have a look at once we've said goodbye, and we'll try to respond to quickly on the chat, and we could always take those conversations offline. Please do complete the feedback form, which Ems has posted. We'd be really grateful. It enables us just to do a better job next time. Do join us next for our webinars on conjecturing and generalizing. The secondary one is Wednesday, the 19th of June. And there'll be more details following about that on our events page. This recording will go at the top of the guidance page. So if you wanted to refer it to colleagues or watch it back again, you're free to do so. Thank you all very much. And we wish you a very happy rest of the day.